Good morning, Professor.
Good morning, Rita. How are you?
I'm fine, thank you. And you? We get as Eden?
Yeah, I'm fine too, thank you. So you can hear and see me without
Yes.
technical problems? Wonderful.
Yeah, I can hear for your voice clearly.
Okay, that's very good. So when we start, you will introduce me or should I introduce
Yes.
myself?
Yes, I will introduce you and then you come directly to the presentation.
Okay, and I
But,
know how to operate.
okay. But we will wait some more minutes, please, Prof.
No problem. I just wanted to know if the technical background is working
Yes.
correctly. Fine. Then I will
We
wait.
the conference already 6 hours ago.
Okay. So
Yes.
everything is fine.
Yeah, the problem is of course with the internet connection,
Yeah.
because the weather is also not so good in Banda Aceh. We have
Okay.
rain and strong winds.
Yeah.
Yeah, but until now, the electricity is okay.
Okay.
I hope because it is very important for us to have
Yeah.
electricity.
Yeah. We hope the best.
I mean,
Okay. Then I will wait for another 10 minutes and then
okay,
we start.
okay.
Thank you.
We are waiting for Dr. Amro also, Dr. Hassan.
Yeah.
Dr. Hassan.
Okay.
Oh yeah, Professor, did you receive what we sent to you?
Maybe I don't know yet because I'm not in the office today. I'm working from home
Okay.
because I have a better connection here.
Yeah, me too. I work from home.
Yeah. So I guess it will be in the office by now.
Yeah.
Thank you very much for that.
Yeah, you are welcome.
There's also the problem that in the office I'm not allowed to use Zoom
Okay. Okay.
because it's a question of data policy because the server
Yeah.
of Zoom is not in Europe, it's in United States, and that's the reason why we are not allowed to use Zoom at work
Yeah.
normally. So I'm doing it from
Um,
my home office.
did you try to use like our virtual backgrounds from homes?
I tried it, but since I have not installed the app of Zoom, I'm not able to put it in because this option is not offered in the browser-based solution. So I'm sorry for that. You have to look on my ceiling.
Okay. No, no, it is not a big problem, and no problem actually.
Okay.
No. And you know
It's a
the
one-day club. Yeah,
yes, bro.
go ahead. Hmm?
You know, in Banda Aceh, at the moment, the increase of the to say the person who infected by COVID-19
Yeah.
at the moment is in the peak position, I
Oh,
think.
okay.
Yeah. So um, yeah, actually, we to say it is not a new normal for us. You
Okay.
see, we have different condition.
Yeah. In Germany, the numbers are climbing again too.
Okay.
We have
Yeah.
about 1,800 to 2,000 infections per day because all the people are coming back from their holidays.
Also, so then like the door is open for the virus.
Yeah.
The holiday.
One more technical question. When we start, should I open up my presentation immediately?
Yes, Prof. You can open your presentation. Maybe that is better
Yeah.
for you, for you comfortable. Yes.
Okay.
I
I will
try
open.
to study that. I read maybe 3 times
Yeah.
for myself. Yeah.
Okay. I'm trying to share it. Can
Yeah.
you
It
see it?
looks very nice. Yeah.
Okay. Wonderful. Then I hope everything will go fine.
Yeah. I hope so.
I have to admit, this is my first digital presentation on a conference, so I'm a little nervous.
Okay. Really. Yeah? Okay. Yeah. Hello. Okay. You start to record, please.
Okay, Rita, you are telling me when I have to start. Okay?
Okay. So I will stop your sharing first, Professor, and
Mm-hmm.
later on, please share again. Okay.
I didn't get that. What?
I stop your screen already for a moment, but later on, you can share again.
Okay.
Okay. Because they inform me that the MC is ready now to open.
Okay.
Thank you very much for the time, Mr. Juzaili Ridwan and Miss Anna Bisco. Assalamualaikum warahmatullahi wabarakatuh. Ladies and gentlemen, good afternoon, and special for our professor. Good morning, Guten Morgen.
Good morning.
So, uh, it is an honor for me to be a moderator for our session, for our discussion session. Yeah, and to introduce myself, my name is Rita Khathir. I graduate from Agricultural Engineering Department, Faculty of Agriculture, Universitas Syah Kuala. And then I graduate my master and my PhD from German University, George August Universität Göttingen. And now I'm working as a lecturer at my alma mater. Okay, and now we want to welcome our professor, Professor Jens Karl Wegener. He comes far away virtually from Germany. You know that the distance between Banda Aceh and Germany is about 9,000 kilometers. And now we can see our professor directly, of course, but virtually. Let me introduce you all about our professor. At the moment, our professor is a head of Institute for Application Technique in Plant Protection of Julius Kunst Institute, JKI. He is also a head of Advisory Committee for JKI approval of plant protection equipment, JKI Fachbeirat, Geräte, Anerkennung Verfahren. And he is also a head of meeting for Fachreferenten für Anwendungstechnik. Professor is also a member of German Phytomedical Society, DPG, member of NOM Group for Agricultural Engineering, and member of VDI-MEC Expert Committee, Research and Teaching. He is involved as editorial board of the journal Landtechnik, Agricultural Engineering, and the Journal of Cultivated Plants. His major in plant protection and animal health, horticulture, and environmental sciences, with expertise in production, risk assessment, greenhouse gas emission, fuel cells, biogas, pesticide application, and shipping of wood technology. And now, we will listen to our keynote speaker, Professor Karl Wegener, with the topic of spot farming giving sustainable intensification a face. Professor, the floor is yours.
Thank you very much, Rita. Good afternoon, ladies and gentlemen. I will start sharing my screen. Can you see the presentation?
Yes, Prof. It is very clear.
Wonderful.
Very clear.
Then I will start. Dear audience, dear ladies and gentlemen, it's a great pleasure for me to give a presentation on the International Conference on Agricultural Technology, Engineering and Environmental Science 2020. Many thanks to the organizers inviting me and giving me the possibility of presenting our research. My name, as already stated, is Karl Wegener, and I'm the head of the Institute for Application Techniques in Plant Protection at the Julius Institute, which is a federal research center for cultivated plants in Germany. The title of my presentation is Spot Farming, Giving Sustainable Intensification a Phase. Within the next 30 minutes, I will share our ideas how we can maintain or even increase yield by reducing the input of resources at the same time. Doing this in a sustainable way seems like trying the impossible, but up to now, we are convinced that we can achieve the goal. From 2015 to the end of 2017, 3 German research centers located in Braunschweig, Germany, together worked on a project called With Autonomous Agricultural Machinery Towards New Cropping Systems. Aim of the project was to derive different possible scenarios for future agricultural systems for plant production under German conditions. Background for this are new developments in terms of digitalization, automation, big data approaches, autonomous tractors, etc. The derived scenarios should be assessed from an economical, technical, and agricultural point of view afterwards. Out of a number of different scenarios, we developed 2 based on autonomous field robots. Both differ concerning the size of the robot concept. We had a large size concept based on autonomous tractor systems and a small sized concept based on field robots. Today's presentation will focus only on the small scale robot scenario. Reason for that is that at some point of the project, we realized that the changes we wanted to achieve towards new cropping systems are not possible with established machinery. Hello?
Yes.
Can you hear me?
Yes.
Yes,
Just
we
continue, Professor. I'm sorry.
Okay. I come back to the presentation.
Yes, please.
Out of a number of scenarios we developed, two based on autonomous field robots, and both differ concerning the size of the robot concept. We focused on the small scale concept because we realized that the changes we wanted to achieve towards new cropping systems are not possible with established machinery. Moreover, to reach the goal of developing new cropping systems, we were convinced that we had to ignore technical development completely at the beginning, just focusing on the needs of cultural plants. The project was also driven by today's challenges we are facing in agriculture all over the world. We have growing population worldwide, we have to feed, we have degradation of arable land, climate change, foreseeable shortage of resources, and many more. These problems have to be solved in a socially acceptable way. This becomes more and more difficult in our days against the background of a society where a majority of people have no more idea how their food is produced and where it even comes from. In Germany, as in many other countries with industrialized agricultural production systems, we are in a crisis. We are facing a lot of concerns and problems addressed in public discussions towards the farmers. People in general are concerned because in their eyes farmers contaminate the drinking water with nitrates, they are poisoning food and feed with pesticides, they torture livestock animals, they ruin the health using green gene technologies, they devastate the landscape by seeding monocultures, they make people scary with their big machinery in traffic, they increase the energy costs by building socially funded bioenergy production capacities, they are all subsidized by society due to public funding, and moreover, they produce a lot of greenhouse gases, suffering from climate change at the same time. Even though I do not share all of these arguments completely, and even though they are pointed out, to some extent, a few of them are based on real problems. For this reason, proceeding agriculture in a way we have done in the past is no future strategy. Change is strictly needed. Before starting a project such as developing new cropping systems, one has to define the goal. In our case, the goal is sustainable intensification. What is the idea of sustainable intensification? It is to increase the output while decreasing the input at the same time. The graph shows an agricultural production function. You can see it here. Yield is increasing with increasing use of resources, such as water, nutrients, and pesticides, for example. This is the common strategy of agriculture in the past. With this strategy, one moves from point 1 to point 2 on the graph. But with climbing resources, the gain in yield, which you can see here, is decreasing. So at some point, it makes no more sense to raise the input. To move towards higher yield without raising the input, as you can see in point 3, or even by reducing it, point 4, we need another production function. And this can be achieved, for example, by different innovations. But additionally, In order to increase public acceptance for agriculture, various secondary objectives have to be respected. For example, the enhancement of ecosystem services provided by agriculture, such as biodiversity or linking of habitats and diversified landscapes. The question is how we can reach the goal of sustainable intensification with simultaneous consideration of social demands. In the past, I'm convinced that agricultural machinery defined the framework for plant production systems. Today, we need a change of perspective. We need to focus on the plants. In order to do so, this mentioned change of perspective is necessary. To increase yield, fundamental requirements of crops have to be satisfied. Cultivated crops have to fit to the location where they are planted, and functional elements of landscape, such as hedges, ditches, and wildflower areas, have to protect the cultivated crops. These three different levels, single plant level, field level, and landscape level, have to be considered. On single plant level, we need to fulfill the basic requirements of cultivated plants, as you can see here. They need sufficient light, space above and beneath ground level, water, unspoiled soils, nutrients, healthy and wide-range crop rotations, and plant protection. On field level, we have a general need for the reduction of agrochemicals, such as fertilizers and pesticides. The soils should be protected against heavy loaded crossings, especially with high wheel loads, and we also need a better consideration of small-scale climatic conditions. Concerning the landscape, we have to develop structures being harmonized to natural, geographic, and climatic circumstances. They should protect the crops against wind and soil erosion, as well as transfer of agrochemicals to non-target areas. Refuge and buffer zones can help to interconnect different habitats in order to increase ecosystem services of agricultural landscape. Smaller structures leading automatically to higher diversification of landscapes can also help to gain back public acceptance. So the new cropping system we are looking for should combine all these requirements and restrictions on the three stated levels to reach the goal. And this is a non-trivial challenge. So the big question is how we can reach this goal. Before I start to present our solution, I will state another 4 hypotheses which are of main importance to find the right cropping system. First, we need to improve the allocation of cultivated crops to suitable locations. I will give you a simple example. A wine grower would not have the idea to plant his vineyard on the north side of a hill. It just does not fit under consideration of yield, quality, and taste of the product. In the broadest sense, this is exactly what we are doing with a lot of cash crops in some regions. They are planted in locations where they just do not fit to the available natural resources. But with help of fertilizers, pesticides, and drainage or artificial water supply, they are forced to grow and produce yield. And I think that this is not a very sustainable way of producing food and feed in a long-term view. Second, the management of natural resources such as water, light, and salts has to be optimized in terms of spatial and temporal utilization. One example, in Germany we are growing sugar beets to produce sugar, and if those sugar beets are seeded just a few days earlier, one has a significant impact on yield. There are different reasons why this is not always and everywhere possible. For example, climatic reasons like danger of late frost periods in certain areas, but there are also reasons concerning the trafficability of the fields. If they are too wet, big tractors used in our days cannot seed the beets without damaging the soil. And if we would have lighter techniques, they could be planted earlier and we could increase yield by doing this. Another example, the natural offer of sunlight on a certain area is given and we cannot influence that. What we can influence is the architecture of the plants growing on that certain area. If two crop varieties with different heights and different leaf orientation are combined, the efficiency of photosynthesis per square meter can be improved. We also can improve the distribution and stand density of the plants in order to increase yield. Third, we need to improve the efficiency of agrochemical utilization. Today, we are doing a lot of research on site-specific treatment of plants, for example, with fertilizers or with pesticides. And first applications are in agricultural practice. In future, I'm convinced we have to go ahead and we need a single plant treatment. Fourth, the general structure of our landscape has to be changed towards smaller elements, more structure and diversity. We need to re-implement functional elements such as hedges, ditches and spots of grassland with bloomers because they fulfill some of those ecosystem services we are lacking of. So in many cases, the characteristics of agricultural fields are not homogeneous all over the field, concerning, for example, soil type, yield, water supply, altitude profile, geographic orientation, potential of erosion, etc. But by superimposition of these individual characteristics, one can derive spots of nearly same properties. These spots, being homogeneous to the greatest possible extent, can be cultivated independently from each other. And this is what we call spot farming. I will give you a simple example below. On the left side, you can see an aerial image of a field. And due to the different colors of green you can see, one can already imagine that this field is not homogeneous in its properties. And under consideration of information, in this case a very simple example, we only consider two information about yield and soil type. We can derive homogeneous spots. as you can see on the pictures on the right side. And these homogeneous spots are homogeneous to the greatest possible extent. And how can we use this information? Actually, such field maps could be used for site-specific treatment, such as working with different seed densities per spot, for example, or for different fertilizer or pesticide strategies. In our approach, we go a step further. We want to have different crop rotations on each spot, which are fitting the best to the properties of each individual spot, what you can see on the right side. Another idea and part of the system to reach sustainable intensification is to optimize the crop spacing. In a triangular seeding pattern, which you can see on the left side, each individual plant has maximum spacing above and beneath ground level. And this also goes along with a maximum of irradiation by the sun. In a triangular seeding pattern, the number of seeds needed per square meter is much lower compared to a row seeding pattern. It's approximately a little more than half as much as compared to the row seeding pattern. This automatically leads to a reduction of seeds as well as seed dressings needed. Thinner seed patterns can have phytosanitary advantages, and each single plant can be more competitive. This can also lead to a reduction of pesticides needed, and it's an interesting question we are just doing research about within the last 3 years. Another point is, and that's a technical point, that one can drive through a triangular seeding pattern in 3 different directions. And nowadays, mechanical techniques come back into the market because society does not want to have chemical treatments. So this can be an important advantage because the weeds standing within the intra-row section can be weeded without complex and cost-expensive sensing and computer-steered systems for detecting and eliminating the weeds. It can work very simply. But this requires georeference seeding technologies with high precision concerning seed deposition, also in relation to the depth for more uniform sprouting of the cultural plants. And this is something we are lacking of at the moment, and where we have built a prototype for our research so far. Triangular seeding patterns also have an impact on the aim of plant breeding. Today, genetic resources are most often invested into tolerance and resistance of cultivated plants against diseases, which normally goes along with decreasing yield. Our hypothesis is if a new cropping system can help to strengthen natural defense mechanism of cultivated crops and at the same time can lower the phytosanitary pressure, then we can shift genetic resources towards yield. The problem up to now is that no one by now knows which characteristics of different cultivated plants are the most advantageous in a triangular seeding pattern. The focus of breeding was on row seeding patterns in the past. And this is a question we are just trying to find out for different grains. Talking about fertilization and plant protection, we have to come to demand-driven solutions on single plant level, as already stated, in order to optimize the input of resources. This goes along with an early identification of plant diseases, pests, and nutrition demand, done by constant monitoring. Once demand is recognized, fertilizer and pesticides have to be deposited in a way that they are completely absorbed by the cultivated plants. And this requires high definition information as well as techniques for precise deposition of fertilizers above and underneath ground level, respectively for the precise application of plant protection products. Up to now, I have upraised a lot of requirements, and maybe some of you are already concerned about the question how this can be realized. I think it does not need a lot of fantasy to imagine that today's agricultural machinery is improper to work on small and amorphous spots, as you have seen before. For this reason, after having derived ideas for new cropping systems by ignoring technology, now we have to focus on technology. And in our eyes, small autonomous robots working in swarms, performing different processes while coordinating themselves, could be a suitable technique for new cropping systems as presented. The low performance capability of a single robot can be compensated by the number of robots being used. Theoretically, robots have an operational readiness of 24 hours at 7 days a week. Robots waiting only a fraction compared to a modern tractor, they have much larger processing windows concerning soil protection and trafficability of soils. These properties can help to improve the overall performance capability of small autonomous machinery. Moreover, the presented spot farming system raises yield by optimizing crop allocation as well as local field management. Even those processes being managed by very large size machinery, such as combined harvesters, can be managed with small robots also. If the combined processes, like in this example, cutting, collecting, flailing, chopping, and spreading, are dissolved again, then we can do the process also with autonomous small-scale robots. In our project, we wanted to know if a process chain with small autonomous robots generally is able to do all annually work in cropping from a technical and economical point of view. In order to check, we choose a scenario of a production of wheat on 150 hectares in a crop rotation with corn. For this scenario, we defined different requirements, which you can see on this slide. The requirements are a tillage with a working depth of at least 20 centimeters, a precise deposition of 150 to 200 seeds per square meter, the application of fertilizer and plant protection products to single plants, and a processing and transport of 20 tons of material per hectare during harvest. When we started our project in 2015, only few robots were used, mostly in scientific projects. Today, first solutions have appeared on the market and farmers can buy those systems. They differ in design, concept, and size, and most of them are only applicable for one type of working process. But there are still big challenges concerning the practical utilization of autonomous field robots. What is the optimal concept, modularity, and size of a field robot? How do they work under practical conditions? How safe and reliable is the autonomy of the working process? What safety requirements do we need for practical use? Which solution is best for energy supply and what infrastructure is therefore needed? Those are all questions we cannot answer yet. And in our theoretic approach, we did not focus on these questions, although they are very important. What we came up is with different robots concepts designed by students from the Technical University of Braunschweig. We had different concepts for different purposes, and they were designed with the help of a CAD program. And here you can see 5 robots being chosen at the end. The number of robots being necessary to produce wheat on 150 hectares is depending on area efficiency of the concept and provided field working days. In the table, you can see the number of robots needed based on this approach. And the number is also depending on the size of the robot. The ones on the left side are bigger ones, and the one on the right side are rather small robots. In the next step, the cost of each robot concept was calculated under consideration of all elements known from the 3D models within the CAD program. And from this information, at the end, the operating costs were calculated, derived from numbers and cost per robot. These operating costs are shown in the table, and they are compared to average operating costs of today's machinery in Germany from literature. And what you can see is that the operating costs of a robot scenario is or can be competitive. And this is the main outcome of our research project. But we still have to admit that this scenario is just a rough estimation. And as I already mentioned, there are tons of questions concerning the feasibility of robot concept in practice. But the general approach seems to be at least an option worthy to think about for future. And moreover, the scenario we use, the cultivation of wheat, is compared to other cultural plants such as root crops or vegetables, much more challenging in the processes we have to deal with. And at the moment, on the German market, we can see that there are quite a lot of companies entering the market with robot systems being sold to farmers for certain purposes. And the prices for the robots are quite comparable to what we have calculated for the big ones on the left side. So we are not too far from reality with our approach. So let me come to the conclusions. What we found out with our approach is that sustainable intensification can be possible, even with regard to socially demanded restrictions if we focus on new cropping systems. The machinery needed for new cropping systems are probably small autonomous robots, which are basically able to manage any agricultural process. and whose operational costs are comparable to modern machinery. Autonomous robots are under development in science and companies, and first concepts, as already mentioned, have entered the market by now. And those autonomous robot systems have a lot of advantages. They can replace labor not being available anymore at the market. In Germany, for example, if you have to weed your sugar beets by hand, you don't find any people who would like to do that. Also during harvest in vegetable or fruit production, farmers can hardly find any workers anymore doing that. Robot swarms can lower the risk of machine breakdown because if you have a robot swarm with a number of robots and one machine is breaking down, the other ones will still work on. They have abilities for new cropping systems, which I have showed to you, like the spot farming concept. And also interesting due to the low cost concept and the autonomous mode of operation, they can also be a solution for small scale farmers. In Germany, we have quite a large number of farmers who are not farming, which is not their main job. They work in a job and they, let's say, have like 10, 20 or 30 hectares of land, and they do the farming at the evening. And for those small farmers, this can be also an advantage if we have autonomous robot concepts helping them to give their small farms a future. Okay, at the end, I would like to thank my colleagues for the joint research project and you, the audience, for your kind attention.
Thank
So
you
if
very
you
much,
have
Professor.
you're
Yeah,
welcome.
you did a very nice presentation, and your time is very precise. Thank you very much. And in for our discussion, we already invite the participant to give you some questions.
Yeah.
But due to the limited time, we ask them to write down the question. So now I have some question with me. I will share to you. This one, Professor. Um, for the first uh, discussion, we have three questions. The first one is from MIST. The institution is ERRD. And the question is how we can effectively this innovation um, dissemination to increase cropping index due to the pandemic COVID-19 era. And the second one, Professor, small autonomous robot is also sweet for small scale farmer. Since we have this culture, our farmers have small land and between the land there is no road. So what is your recommendation then for our country? And then the third question is from Miss Yovita, the same institution with Mr. Maisti. Does it is also applicable to be executed by small scale farming, considering the diversity between location of farming? What the crucial aspect should be underlined when we want to implement in different areas, particularly for small scale farmers? So I think there is a correlation among these question because of the different type between the farming in Indonesia and the farming in Germany. So, Professor, please answer to this question.
Yeah, thank you very much, Rita. Um, as I already mentioned, we have in Germany also these very small scale farmers, and they also have their land, which is distributed in different areas. So we are talking about a few kilometers, which they are away from each other. And in the concepts we have so far, entering the market or being in under development in science, there are mainly two concepts how to move those robots. One is to put it on a trailer and drive it to the field, and depending on the sizes is uh, one way how to handle it. Another idea is that those autonomous robots be allowed in future also to drive autonomous to the fields by themselves. But this is something where we have to still have to define the legal requirements for autonomous driving, and most of them are able to um, drive on off-highway or all-terrain fences, so that one can put the robot from one field to another by driving it by hand, by example. You can have a controlled steering of those robots, for example, and you can drive them by hand from one field to another. I have to admit that I don't know the situation in your country, how the terrain looks like if there are no roads, but this is a good question we have to manage on. How does the system can look like where those robots are used in the whole process? Also the question, how many people do I need to operate these robots? How is the um, distribution concept, and all the questions I have addressed towards um, reliability, safety requirements, and so on. And this is still in work.
Okay, Professor, thank you. And we will see the next question. I think we still have time. From Mr. Agustomi Sitorus, the Nation Institute of Science LIPI. Dear Professor, I'm interested in your presentation related to problems in agriculture, namely the contamination of drinking water with dangerous chemical resulting from fertilization. My question is, how badly has this contamination gone on farms, and can you share how we can measure in the field so that we can reduce the level of danger?
Yeah, thank you. Also in Germany, we have some locations where we have higher problems with the contamination of drinking water. Those are those regions where we have the uh, production of cattle and pork. They are concentrated in the northern part of Germany in a small region. And there we see that farmers put lots of nutrients on the fields from the animal production system. And this is something we have to solve for the future. And at the moment, we are trying to to drive the nutrients all over the country, sharing them on farms with no animals, but this is not very efficient. And our idea is that we would like to, how do you say, optimize the manure by processing it, taking out the water. So we have a lot smaller fraction, and then putting it on the field um, in the best way directly beneath the plants, so that the plants can have direct access to the nutrients. And there's a lot of research done in the last years that, for example, in corn, if you put the fertilizer beneath the plant directly, you can like reduce the amount of nutrients needed by 50% without decreasing the yield. So we have to get better on the deposition of the fertilizers. Today we spread them on the field, and lots of them are not going into the plant. They are going in groundwater bodies, or they are going away by after rainfalls. And this is something we have to optimize. And I think this could be an option, doing that with robot systems.
Thank you very much, Professor, for your answering. And really, we have some more questions. Uh, but due to our limited times, I promise to send you the question. So
Yeah.
then maybe we can give the answer, the feedback to the presenter who show the feeling of interesting to your presentation. And hopefully this one is what we expect to be the outcome of our conference.
Okay.
And ladies and gentlemen, in the morning, we listened to the idea about smart farming, and now we listen from our professor about spot farming. I think these two knowledge for us today is very related each other in order to face the revolution industry 4.0, especially for the development of agriculture. And Professor, it is an honor for us to have a scientific discussion with you. And what can I say? It is a very expensive discussion, actually, expensive time for us. And we hope that this result will benefit for the future experiment and give positive contribution to the country. And it is very important to be strong, or more powerful by having knowledge. And I remember one wonderful German quote: Nur die Harten, kommen in den Garten. So only the strongest will we survive. And now we are in a very hard condition, pandemic COVID-19. And Professor, vielen Dank for your presentation, for your knowledge. And I would like to invite the MC again, because they will guide the process of handover uh, something for you. So please stay with us for the next 5 minutes.
Okay, thank you very
Please,
much.
Sometimes.
Mr. Juzaili Ridwan and Miss Anna Misko. Again, maybe we have some things. Professor, you see that the participant is almost 200. So we have and 50% of them all presenters.
Yeah.
And the rest is my students.
Okay.
I want to ask something, Professor. Is it okay?
Yeah.
Miss Rita,
Okay,
okay?
please.
I want, okay. It's very happy to know that we will have autonomous robots with a lot of advantage. But I didn't get information from your explanation that the robot we can use it in land area because in Indonesia, like in Kalimantan, we have peatland area. Peatland, you know, peatland. If we planted rice in peatland, it
Yeah.
will be a problem. Many problem there because the peatland when we go to the peatland, it will shrunken us.
Yeah.
So peatland, is it the robot we can use to the peatland area also for planting rice?
First of all, let me say the following. The robots I have shown are only theoretical concepts. They have just been designed in the computer and they are not really they have not really been built. But on the market now, we have some concepts built by companies, and they look like those robots we have developed. And they are constructed for German conditions. We don't have peat soils in Germany, so there's no need to have a design being able to operate on peat soils. But if there's a market for type of farming, then I'm convinced that some company will focus on that and they will find solutions for that. I've read a paper about, I think it was from Japan, where they had a robot, a swimming robot for rice fields, and I don't remember what the purpose of operating was, but it was focused on the operation in rice fields, and very important product worldwide. And there will be solutions also in this area, I think. It's a matter of time.
Yes, but it's possible. It's very, very possible.
I think so.
Yes, I think. Because in Indonesia, is the wetland only in Kalimantan, and Kalimantan is consists of peatland.
Yeah.
Yes. In another place of Indonesia is only a little land for the farmer.
Yeah.
So to use in Kalimantan.
In my eyes, autonomous robots have the great chance to substitute manual operating systems, all the things the workers do by their hands. This can be probably subsidized by small autonomous robots. And this is what I tried to say using this example of the combine harvester. Like 100 years ago,
Maaf
when
ya,
we
ini
did
udah
not
bisa
have
dengar
a
lagi,
combine
Ibu?
harvester, the people had to chop the grains by hand, they had to collect
Ibu hilang
them, they
koneksi
had to
tadi.
flail them by hand,
Sorry.
and they did it one step after another. And
Oke,
In
jadi
a
kita tadi
combined
sudah mau
harvester, we
menghitung
combined all those processes in one machine.
ini ya,
And this is
nilai
why this
rata-rata.
machine is so huge. But we have the chance to also do that with small
Caranya tadi
robots
kan
if we
sigma I sama dengan 1
focus
sampai
then
9
on
dari
single step,
FI, XI.
and
Jadi F
then
tadi
we will be
frekuensinya,
able
XI
to do it all
nilainya
with
kan.
small
Kita
machinery.
jumlahkan, nanti kita peroleh 60,
And
dibagi dengan 10 dapat 6.
in my eyes, all these hand-operated working
Kemudian
processes could be
kalau kalian
also
mau cek,
substituted by
kalian juga
robots.
bisa lihat apakah betul mu X bar sama dengan
Although
mu.
there are very different circumstances if you work on peat soil or on other arable
Dengan
land,
langsung
the
mencari 2
design
tambah
just
3 tambah 6
fit to the
tambah 8 tambah
circumstances.
11 ya.
And why not having a
Mu.
swimming robot?
Kita cek ya.
For
2
Yes, very nice.
tambah 3.
It's very nice because consider our land is our land unit is very ergonomic, not the same.
2 tambah 3 tambah 6 tambah 8 tambah 11 dibagi 5.
Very
Jadi
functional.
harusnya dia sama tadi dengan
It
mu
will be built in
simple ya.
2015.
Jadi ke depan juga kalau lebih mudah kita ngambil yang dari populasi tadi karena populasi sedikit ya.
Commercial product,
Namun untuk standarisasinya berbeda ya.
robot.
Jadi nggak boleh di
our robot
langsung
system I have
dianggap
shown, as I said, are
standar
only
deviasi
a
populasi sama dengan
theoretical
standar deviasi dari
only designed
sampel.
by computer.
Oke, sekarang untuk standar deviasi daripada sampel, nah kita betul-betul harus dari yang sampel ya.
On the
Sigma I sama dengan 1 sampai 9, FI,
technical shows, like I don't know if you know the
XI
ICATES,
sampel dikurang dengan mu
world's
X ya,
biggest
rata-rata kuadrat. Dibagi dengan
how do you call
akar
it?
dari sigma I
Fair
sama dengan super
for
N dari FI, itu tadi sigma
technique,
N
and
kecil
it's
ya.
in Germany, and in
Nanti kita peroleh, kalian cek
2013
nih berapa di sini,
I
berapa
saw
di
the
sini
first
diisi ya,
robot
dari
concept
sini terus dapat
shown
nggak?
by a company.
Konfirmasi
In 2015,
2,01.
every 2 years, the Agritechnica, there
Apabila
were
ya,
a handful of robot concepts shown by different companies.
ternyata itu apa namanya dengan
On
tanpa
last year's
pergantian tadi pakai
Agritechnica
faktor koreksi itu
2019,
saja
there were
pembedaannya.
first robots
Nanti
you
dibandingkan
could actually buy.
kalau kita kasusnya sampling tanpa pergantian dengan
And so
pergantian
the
akan dapat di
development
sini
is
nilai standar
very quick.
deviasi yang baru. Itu
And
saja N-nya di sini, N kita tadi 5 ya.
what will be shown next year on
Populasi
Agritechnica,
sementara
and
sampelnya itu kan
I
setiap
guess
itu 2 tadi,
the
N
number of
kecilnya sama
robots
dengan 2.
will be lot higher.
Oke.
But
Kemudian kita lanjut,
in
diketahui
my
amatan
eyes,
satu populasi
the
adalah
problem at the moment is that those
2,
companies
3, 6, 8,
focus
dan
only
11 ya.
on one
Hitunglah min
operation.
dan standar
And
deviasinya.
what we
Nah,
need
ini ada
is
nih.
a standard
Kita
robot.
dapat
Like
min
we have
atau
the
mu
standard
sama dengan
tractor where you
6,
can
standar
attach
deviasinya
any kind of
3,29.
working principle or tool to the tractor. And this is the same we need for the robots. We need a standard robot where you can
Oke,
attach different tools for different working
kemudian
processes, so
ini
that
terbukti tadi ya,
the
kalau kita dapat 6 ya.
investment into
Di sini
the
juga 6 ya.
robot is
Pas kita cari yang
increasing.
ini juga dapatnya 6.
Thank you, Professor. Thank you, Ibu. Because of the time now,
Sekarang kita lanjut ke teorema
give
limit
the
pusat.
microphone to our MC, please, Mr. Juzaili.
Admit ya?
Thank you very much too.